So for the second talk of the day, we have Sepehr Assadi. That's few passes. Log n. This is optimal for tonight streaming Maximal.
Okay, thank you. Everyone can hear me? Good. Okay, perfect. All right, thank you for coming to the talk, and thank you for the organizers for inviting me. So I'm going to talk about this result that Clement mentioned. It's a bit of a hard result to talk about. I've tried it a couple of times, it never worked. I hope this time it works. And my goal is not to put all of you to sleep, basically. Good. So, and this is joined with Christian and Kiran and University of Bristol, and Janani, who's my student, who was. Good, okay. And the theme of the question we want to understand here is that how much these locality bounds, like we are at WoLA, we are talking about locality, how much these locality bounds translate into other sublinear models which are not necessarily local. And just to throw in a bunch of names, a streaming, sublinear time, MPC, congested click, these are all models that allow some sort of all-to-all communication, whatever that means, that is not local. So you might expect some of these locality barriers no longer exist. And in this talk, I will talk about this question through the lens of MIS, one of the most local, like well-studied problems from perspective of local in the graph streaming model. Okay, and I define this. So independent set, like we all know, a bunch of vertices that have no edges between them. MIS is an independent set that you cannot trivially extend it. So this is not an MIS, but this one is. This talk n is going to be the number of vertices. So there is a very easy algorithm that computes an MIS. You pick an ordering of vertices, you go from left to right and greedily add them to the MIS. Okay. You can also see it as a local algorithm. Just pick the ordering random. Okay. And you don't have to wait for everyone to catch up to make a decision about the vertex. Any vertex that appears first in the ordering can already join the MIS in one go. So in the first time, basically all these vertices know that they are going to join the MIS. So you might as well just add all of them right now already. Okay. Then you handle all their neighbors and then you recurse. Okay. So that's a way of parallelizing this sequential sequence. Okay. And we've known for quite some time that first Luby proved like 40, 50 years ago that some version of this algorithm finishes in order log n. And now at this point, we know exactly this algorithm itself finishes in order log n, rounds with high probability. So we can say that locality of MIS is order log n bounds. But how does this bound translate to other models when we are talking? Okay. And for that, let's look at the graph streaming model. Okay. In this model, I have a graph G. I know its vertices. They are numbers 1 to n. I don't know the edges. Okay. And these edges are coming in some stream like this in some arbitrary order. And what I want to do is to process this graph, use a limited space proportional to number of vertices. Okay. Not enough to store the entire graph. And try to read this stream only a few number of times. Think of each round of a local computation as one pass over the stream, very, very vague. And this model is called semi-streaming model, and it was introduced by Feigenbaum, Kanan, McGregor, Suri, and Zhang. So is the model clear? Everyone happy with the model? Okay. So the first thing, this is homework, basically. You can do it in 5 minutes. The randomized greedy MIS that I told you is also a semi-streaming algorithm, or gives you a semi-streaming algorithm. You can implement each round of it in like 1 or 2 passes, really. Okay, there's nothing, like you don't need any more ideas. Like it's very easy to do that, and you get an order log n pass semi-streaming algorithm. Okay, so you can say that, oh, if I have a local algorithm like that, it gives me an order log n pass algorithm within the same locality. We are happy. But it turns out you can do much better than this. Okay, this is not the end of a story. There's this very nice result by An, Kormod, Goha, McGregor, and Vert that the same exact algorithm, like you can implement it in order log n passes. Okay, so it's the same algorithm. You're not changing anything. You're outputting basically this algorithm. You can say that samples an MIS according to the randomized greedy algorithm. Okay, with high probability, and finishes instead in order log, log, and passes. So you can get an exponential speedup, okay, over these locality type paths. What is more perhaps interesting is that this is not an isolated result. It wasn't a fluke that this happened, okay? This is a general theme at this point. Like, this result led to exponential improvement over these locality bounds across lots of other models. For MIS, for instance, almost exactly the same algorithm works in congested click. Again, an algorithm which is like very, very similar to this works in MPC. Okay, somewhat these algorithms are identical implementation of the same thing, and now we can run them in different models. In fact, it's not even limited to MIS. There are these type of results that you can cast them on the umbrella of round compression, like Arthur, Slobodan, and others have these results for matching in MPC. There's a more recent result we had similarly again for like some approximation of matching, dynamic streaming, that can compress rounds of a local algorithm in all these cases down to some exponential factor, okay, and get better rounds in these other models. So in lots of settings, we can get exponential improvement over locality bounds, let's say for MIS, okay? And I want to emphasize it's and between semi-streaming. But the question we are asking is that can we do even better than this? And now I want to put an or here. Like, I was happy to understand this question in semi-streaming. I was also equally happy to understand it in some other models, like congested click MPC. Okay. Can we do better, basically? And this is what the topic of this talk is about. Okay. And I want to say that different versions of this question have been studied. Like, for instance, Arthur and Yara were looking at this type of question in MPC, for instance, like lower memory, if you can do better, like similar type of result. We are going to look at that through the lens of semi-streaming model. And basically, our result says that, no, you cannot do better than this. Okay. Any semi-streaming algorithm that you have for MIS needs this omega log, log, and passes. So this is the main result. We just proved that basically this improvement, this exponential improvement that we got, there is a limit to it. This is it. You cannot do better than that. In this case, this is an unconditional result. This is like, you don't need to make any assumption like the things you have to do, for instance, in MPC if you are familiar. I should mention that we only previously knew how to prove a one-pass lower bound for this problem. So we knew that you cannot solve it in just one pass, okay? But no trade-off in terms of number of passes. And yeah, this is basically saying that if this type of exponential improvement that we were getting on locality bounds are optimal, at least for MIS, at least in the streaming. And one thing I like about this is that I'm going to say something very vague, but this means that this type of round compression, if you define this type correctly, is not going to work for MIS in other models as well. Okay, you can define a family of algorithms and say that this family of algorithms fit within this framework, and that particular family, you will not be able to solve MIS with that in some other model like MPC. Why am I mentioning this? Because MPC is a model that is notoriously hard to prove lower bound for. Almost any non-trivial lower bound here will imply circuit lower bounds, the type of things that we didn't know how to prove for like forever, basically. So you don't want to try and start proving unconditional lower bounds in MPC. You can prove conditional ones. Some type of conditional is to make some assumption about what problems are hard and use them to prove the lower bounds. This, on the other hand, tells us what type of algorithms I can use, and it's telling me that that type of algorithms will not solve the problem. This I'm mentioning it in case you were interested to talk about this offline later. So does the result make sense? Now, for the rest of the talk, I'm going to try to tell you roughly. Yes?
What is the constraint about the space?
O tilde n. O tilde of n, proportional to number of vertices. Any other question? So now I'll try to give you some idea about the proof, how you can prove this thing. The first step is to cast this problem as a communication complexity problem. Okay. We'll go over it a bit quickly and vaguely because it won't be too important. The way we'll do it is we take a stream, okay? And think of our stream, instead of as running an algorithm over the entire stream, think of chunk it up and give it to like k players. Like the first part of the stream is given to player 1, like some other part given to player 2, etc., etc. The length are not equal. The important thing is that these are consecutive parts, okay? So my entire stream, there's a player that is responsible for some part and the next player for next part. Instead of running a streaming algorithm, these players are going to talk with each other. So player P1 sends a message to player P2, player P2 sends a message to P3. You continue like that, the last player sends a message back to P1. Okay. So instead of talking about passes, I will talk about a round, basically. And it's very easy to see that if you have a streaming algorithm, you get a communication protocol here. You just run your algorithm. P1 communicates the memory state of the algorithm to the second player. A streaming algorithm does not need to see the input beforehand. It just needs to get the memory content and continue running it from there. Okay, that's the whole point of a streaming algorithms. So you can, instead of talking about the streaming algorithms, you can cast it as a communication problem and try to analyze how much communication these players need to do with each other to solve the problem in certain number of rounds. Make sense? And if you prove a lower bound here, you immediately get a lower bound in a string. And our result is that fix any number of rounds you want. Any R round protocol with R plus 1 players needs something which looks like n to the 1 plus 1 over 2 to the R communication. Okay? Ignore this minus 1, ignore the small o of 1 term. You are talking about n to the 1 plus 1 over 2 to the R. Okay? Why is this the type of bound I want? Because I'm interested in figuring out how many rounds I need to solve the problem with roughly n communication. This is telling me for that you need R to be log n. Okay? You need to set R to be log n such that that become n to the 1 plus 1 over log n, which is n-ish. So if we prove this, we'll get the result that we want. And in fact, this gives us a trade-off for the entire range. This is almost optimal for the entirety of values of R, not just for one. Very good question. So let me say this thing first. First, I'm going to lie, okay? And through this talk, we are going to pretend there are only 2 players, okay? The result that is we prove in that paper uses more players. At this point, we know how to prove it even for 2 players, okay? You will lose some factors that like the numbers will be a bit different, but now we know how to prove it even for 2 players, okay? For this talk, really forget about we had many players. We are lying, we just have 2 players and we all accept that, okay? I have Alice and Bob and ages are partitioned between Alice and Bob. Good? So in terms of techniques, let me put, there are 2 almost entirely disjoint sets of techniques here. And that's what makes it very hard to talk about the paper because they are like completely disjoint, but they also have to be related. And anyway, one part is like some combinatorial construction. We have to come up with some graphs that we never found a good way for them. I'm going to call them fractal looking. I know Johnny hates that word. And I've not checked with my other co-authors. So we'll go with that. If you find a better word, we'll take that. They are not really fractal. They might be fractal looking. Okay, so we'll go with that. And then there is also an information theoretic part about the result, which I'll start telling you a bit about here and then tell you what the graph we create and go from there. And putting all this and packaging them together gave us this technique that we call hierarchical embedding. That turns out to be a super strong technique for proving a streaming and communication lower bounds. And since then, we managed to use it to prove some other lower bounds as well. So what is happening? Let's start with the information theoretic part. Okay, and let's start with this notion called round elimination. It's a very general technique. It goes back to this work of Milterson et al. On data structures. And roughly speaking, it's basically a careful induction. It says that if I have an R plus 1 or R round too good to be true protocol, I want to prove a lower bound for R round protocol. And I'll assume that I have a very good R round protocol. And then you somehow look at this and say that, look, it is so good that in its R minus 1 round already it does something magical. So you kind of eliminate the first round of the protocol. And you say that now I have an R minus 1 round protocol, which is still really good. Okay, it might not be as good, but it's still too good to be true. And if you can do that, you continue doing this, eventually you end up with a zero-round protocol, okay, that without doing anything can solve the problem, okay? And that's definitely a contradiction, okay? So you can then go back and say, okay, I couldn't have such a good protocol in the first place. Let's formalize this a bit more, okay? There is one framework of applying this. I'll call it a standard, but there are 10 other ways of doing this thing. I'll just mention one version. Let's say I have a problem P where Alice gets X, Bob gets Y, and they want to solve some problem P in R rounds. I'm going to take that problem and create a problem Q, which is going to be hard in R+1 rounds. Okay. And this problem is like this. To Alice, I give K different inputs of the original problem in P. So Alice has K different large inputs. Okay, these are not bits. These are all of them. Is a large input to problem P. Okay, and to Bob, I'll give a pointer to one of these instances, and his share of input in that instance. Okay, and then I'll ask them to solve that one particular instance of the R-round problem. Okay, so Alice had many. I'll point to one of them and ask them to solve that particular instance. The only thing is that Alice doesn't know what is that particular instance. Bob knows it. Now, if you think about it, if you try to solve this problem, you can do one of these things. Either Alice can communicate at least K bits, so she has had enough chance to tell me one bit about each of these instances. If she does that, then when I talk about this hidden index I, she might have revealed something useful about it, and Bob can use that information. Okay. But if Alice talks even less than K bits, we can say that we might as well Alice just doesn't talk at all, because she cannot say anything important about Xi. So let's just say that she doesn't talk at all. Now Bob starts the problem, but now he only has R rounds instead of R+1 rounds. The first round is wasted because Alice couldn't say anything useful. So we just skip that round and let Bob solve the problem. Alice and Bob solve the problem in R rounds instead of R+1, knowing the index I. Does this make sense? Like at a high level, this seems like a natural strategy if you want to solve this problem. And this main result of round elimination was that this is optimal. Okay, if you want to solve this problem Q, you either have to communicate K bits, or you have to solve the problem in R rounds. The communication you need to solve the problem in R rounds. Okay, and that's why it's a round elimination. Basically, you can relate R round communication to R+1. So this is a standard round elimination. For us, this doesn't work, and I will not tell you why it doesn't work. Okay, I'll just tell you what will work for us. We are going to create another problem Q that looks like this. Alice, instead of having K instances, she has a matrix of instances. Okay, like Q columns, each of them with P instances. Instead of a single instance Bob points to one of the columns and has an input for every entry of that column. Okay, so Bob, let's say that I want to solve this group, and I have an input for every one of them. And the goal of Bob is to output the answer to this problem P for everyone in this column. Okay. Basically, Bob picks a column, has an input for every one of them. These inputs latch onto each other. Okay, and then Bob has to solve P different version of the problem. And what we are proving is that the same natural thing happens here as well. Either you communicate P times Q, so Alice tells me one bit about each of her inputs. If not, and this is the important part, the problem becomes P times harder than the R round problem, because you want to solve P of them, so you would expect it to become P times harder as well. These are usually called direct sum results. If you want to solve P times version of a problem, you might expect it to become P times harder. And proving this thing requires doing some sort of round elimination, using some prior techniques. Proving these direct sum results requires using tools from information complexity. And then finally, combining these two together requires these things called message compression that allows you to move between information and communication somewhat freely. So this was the part which was information theoretic. We do this thing and we can prove this result. Okay. Now I want to move from here and tell you about the graph theoretic aspects that uses this type of lower bound and try to create graphs that can implement this strategy. Okay. And this is where might be a bit, yeah, I don't know. Okay, let me tell you what's happening. I'm not saying I have 20 more minutes. I will not keep you for 20 more minutes. Don't worry. So the goal here is that, you know, this round elimination framework creates a problem PR plus 1 round from a PR problem. Okay, we created these magical instances of the problem. Now I started with some problem, and from P I created this Q that was this matrix, etc., etc. But I'm not trying to prove a separation or something. I'm trying to prove a lower bound for MIS. Okay, I cannot just create some made-up problem out of matrices and prove a lower bound for it. Okay. So the goal is that actually all these problems that I create through these matrices, they all have to remain MIS. Okay, so I somehow have to reduce MIS to itself, maybe on some certain distribution. And for that, we have to pick something like this and make all of this look like MIS. Okay. It's kind of looking like this. So Alice is going to have an input graph GX that has tons of smaller graphs inside it. Okay. For each column of that matrix, I'm going to have lots of smaller. So every entry of that matrix now will become a small graph here. Okay. Then we will come up with some gadget that allows Bob to say, look, none of these instances matter at all. Okay, there is just one column that matters. Then he's going to put his graphs there and create these type of graphs. Okay. And then we want to say that if you were going to solve MIS on the entire graph, you have to solve MIS here and MIS here and MIS here. On each of these things, you have to find the MIS of this column. Okay. So I want to create some graphs that simulate such an argument. This is another place that was like, I have to bring this picture. It was a very, very bad picture. Like I cannot just put my graphs disjoint from each other. That will create something which is very sparse. It's completely useless for proving a streaming lower bounds with O tilde in space. Now this is the leaping part. It's very, like that's the part I always made mistake in previous talk, to convince the reader, to convince people why what I'm going to say next handle this. I will not try to do that. I'm just going to tell you what we are going to do without telling you the intuition, the step bit. We need the following type of graph to be able to implement that strategy. Okay. Suppose you have some target graph on B vertices in mind. Okay. And this is a purely combinatorial question at this point. Suppose you have some target graph in mind. Okay. Let's say triangle. Okay. Even though for us this is going to be much larger. It's going to have like n to the 1/3 vertices. But for now, think of a triangle. So you have a target graph, which is a triangle. You want to pick many, many copies of this graph and put it inside a single graph. Okay. Q times P copy of this graph, and you want to put them inside the graph G. And these copies first should be, these copies of H should be partitioned into Q groups, each of size P, corresponding to these columns. Okay. So for instance, I'm creating 3 groups of 2 triangles each, and I'll show you in a bit how they look like. This is the property of the groups. In each group, in each column, basically, is a vertex disjoint union of copies of H. So it's a vertex disjoint copies of triangles. Okay. Each of my groups, if I look at its vertices, I'm going to see 2 disjoint triangles. This is another 2 disjoint, this is another. The second property is that if I look at this part of the graph, I only see these triangles. There are no other edges between these vertices. Okay. If I look at these blue vertices, the only edges between these blue vertices are edges of these triangles. There are no other edges between them. Like this edge is not allowed to be part of my graph. This is the graph we want to create. Sounds good? And it creates lots of constraints on the thing we want to create, but we still need this P and Q to be as large as possible. Okay. You cannot make them larger than this and make them vertex disjoint because each of them have size b, okay, inside a single group. And there is a similar argument that tells you Q cannot be larger than that. So you want to pack as much possible inside a single graph while satisfying these guarantees. And if you can do that, then this picture that I have, it's not going to look like this. In reality, these things are all packed on top of each other into a smaller graph. But the good thing is that these edges do not exist. You were not allowed to put an edge. This set of vertices, if I only focus on that part, I should not see any other edge. So for the purposes that I had, that Bob is later on going to get rid of this part and try to solve the problem, okay? I will actually still kind of work with that previous abstract picture. So this abstract picture is not too far from reality, okay? For the purposes that we had, if I focus on a single column. So basically, this is not lying too much, okay? It took me some time to do this. Good. And very quickly, I'll skip this part. If you do this thing, there is a nice dynamic that is going to tell you that these are the type of bounds you get. Basically, if you can do this once, you are going to be able to get into the 4/3 lower bound, and then you recurse on that, get the final bound. But very quickly, I want to tell you how these graphs, like how one would construct these graphs, or what is so magical about them. And for that, let's look at the simplest possible example of this family of graphs. So this is not what we need. This is the simplest possible version of these graphs, okay? I'm going to look at this line, and instead of having a graph edge, I just want it to be a single edge. Remember, we need this guy to be a graph on n to the 1/3 vertices. But for this example, let's assume it's just a single edge, okay? So if my edge is a single edge, what will happen? I want to put p times q edges inside the graph. So I have a graph with p times q edges. What does this mean? A group is a vertex disjoint collection of p edges. What is a vertex disjoint union of p edges? It's a matching, exactly. So each of my groups is a single match of size p. And it says that there are no other edges between edges of that match, which means this is an induced match. Now, for some of you who have been in this workshop, in this program, we've talked about these graphs many, many times. These graphs are called Rosa-Zameretti graphs. A graph that has many it has many induced matchings that are disjoint from each other. Already, these are very magical looking graphs that you don't expect them usually to exist. Okay. What we need is a lot more general than this. And what we are doing is basically create a generalization of these graphs. Kind of, they look like taking an RS graph and replacing each of its edges with a copy of H. That's the mental picture you should have in mind, even though that's not accurate. And the reason I've been calling them fractal graph is that the way we create these things, if you look at an R-round instance, we had a graph, and every edges of it we replace with the copies of itself. And then when you go to R-1 round, every edges of that thing has many copies of itself. So these graphs in R-round, there are these places that you can zoom in and you see the same graph again and again inside each other. Okay? They're not exactly like a fractal. You can't go to infinity. It's not everywhere in the graph. There are certain places you can. One last thing here, all of these things that I say actually don't work. The reason is it's an easy exercise that you can prove that you cannot take H to be an arbitrary graph. This I'll encourage you to think about it if you like. You can easily prove that you cannot actually have such graphs when H is like a B-clique, for instance. The good thing is that even though we are taking these graphs to come from our hard instances and they're going to look very complex, they're not going to be entirely arbitrary, okay? They are going to, particularly, have a low chromatic number. We can construct them in a way that when we are talking about R rounds, their chromatic number is roughly 2 to the R. And that gives us the go, basically. So 2 to the R is much less than B, so you cannot put a clique there as such. And this is our second main contribution. Any k-colorable graph H that you give me, we can turn it, we can create this type of graph G, which themselves are also k-colorable. with these parameters that is roughly n over b minus some factor. Okay, so there is a loss. And this loss basically, as long as k is n to the small of 1, this loss is also n to the small of 1, okay, which is okay for us. So we can create these magical looking graphs, okay? And by creating them, then we can go through these lower bounds and do what. And one thing, if you were paying attention, this doesn't lose anything in the colorability, or the chromatic number doesn't change here. But I was saying all round instances requires 2 to the r colors. That's because of the reductions and the gadgets that we are putting there. This part is not losing anything. All right, and their construction uses some KAP free sets. These are similar to these graphs used for additive spanner lower bounds. Then we also have a new graph product that roughly takes a path in a graph and turn it to a graph, which was interesting. With all of that, you'll get this framework and make it work to prove the communication lower bound, and then it gives us the omega log n pass lower bound for us. We wrap up in 5 more minutes, and I'll finish in a minute. So this implies that solving MOS requires log n passes, which is optimal under this result that I mentioned. In the last couple of years, we managed to prove tons of streaming lower bounds. And if people are interested, I had some short survey in SIGAC News listing some of them. This was the first time we got to the stage that we can prove even optimal lower bounds for the problems. Like, we were mostly building tools, and now we are at a stage that we can use them and prove lower bounds. This was one actually parallel to this. We had a work with Jujan and Gilad that proves roughly log n pass lower bound for MST in dynamic stream. And then some combination of these techniques more recently with Sohail and Janani, Christian and Kiran can prove log n pass lower bound for matching in dynamic stream. In fact, we also prove this is optimal. John is giving a poster on the algorithmic part of this, if people are interested. And the final, or the main open question I have in mind here is that going back to our original question of what is the connection between locality in these models, can we extend some of these ideas and say something meaningful about MIS or some other problems, these other models like MPC and congested? We cannot prove lower bounds here unconditionally. These are circuit lower bounds, but maybe we can say something. Okay, it will be interesting to explore that. That's all I wanted to say.
So maybe ask the questions for the But yeah, let's thank again Sepehr and Sophia for their talks. Yes, see you at 11. There. Yeah, I saw the 10 minutes later. 7 minutes late. Yeah, exactly. This is not something I couldn't see your legs. I know.